Hi, today we're going to have a look at an IBSL question from topic 7, which is nuclear, particle and atomic physics. So the first part of this question is about beta plus decay. It's a 2-mark question where the first part of the question, first mark will come from us getting the format of the equation correct, and the second part is awarded for getting the right product. So here, phosphorus 30 will decay into silicon 30. Note that the atomic number will decrease by 1 because a proton here is decaying into a neutron, emitting a positron, which has a charge of +1 and has a mass of 0, plus an electron neutrino. Now you don't really need that subscript, but it's a good idea to put it in. The second part of the question is a 3-mark question, and it's asking us to draw a Feynman diagram for this for the same reaction. So here they've already given us an up, down, up quark composition in the bottom. We should recognize that's a proton, and it'll decay into a neutron, which is made up of 1 up and 2 down quarks. So one of those up quarks has to decay into the down quark. Now the weak force is responsible for this interaction, and it's actually the W plus boson. It's worth remembering which boson it is as well, but it's also pretty easy to figure it out. So we should write down W plus, and this will emit, like we said before, a positron and an electron neutrino. Now the arrow for the electron neutrino should go outwards and forwards in time, but the positron, because it's an antiparticle, we actually make the arrow go into that vertex there. Be careful. If you get the direction of the arrow wrong, you will not be awarded that final mark. So the third part of the question has described a scenario for us, which is energy is being transferred to a hadron in an attempt to separate the quarks, but we don't actually see that happen. And that's called quark confinement, which basically states you can't really observe isolated quarks. We can't really see an up or a down quark by themselves. So to answer this, we need a 2-parter. So the first part will be as energy is transferred to a hadron, what we actually see happening is new particles are actually created, which we saw in the previous 2 parts of the question. We got a positron and we got an electron neutrino. And this happens instead of quarks being, of the hadron being separated into the quarks, or their constituent quarks really. And this is actually a consequence of the strong force. You don't really need to discuss the strong force here to get that second mark. You just need those 2 parts describing what happens and why it happens. And that should be sufficient for 1C. So the final part of this question, it's a little bit of a silly question, but it's an important one to consider as scientists. So the standard model was accepted by many scientists, and they're asking us, why is it important to continue research or continue testing basically an already accepted model? There's lots of reasons for this. Number 1, in science is we really want to test to see if we can find a mistake in a model. That gives us more confidence in a model. Number 2, as time goes by, new technology is usually developed. And as a result of this, we might be able to detect or find new information or get results we didn't have the means of getting before. And this new information might just provide us with new insights for how to either change a model or to revise a model, or what improvements need to be made to an already accepted model. So in this part, just anything along the lines of, models we need continuous testing, or anything along the idea of improvements and revisions always being required in scientific models is really what they're after. And with that brings me to a conclusion to this question. I really hope you found that helpful. I'll see you next time.